Okay, so this is section 3 of chapter 2, and now we're really going to dig into polynomials and their graphs and just information regarding polynomials. Every year students get a little bit nervous when they see this. Don't worry, this is not a formula you'll have to memorize or plug into or use, but what it is the general form of a polynomial. Now, this number right here, the one in front of the term with the highest degree, this is our leading coefficient. And then this term right here, this n, tells us the degree of the polynomial, the biggest exponent. Now this term at the end is our constant. Zoom in a tiny bit for you guys. And that's just the general form of any polynomial. So this equation here describes all polynomials. All right, and terms are in descending order here. So let's look at some examples of what polynomials are and what they are not. So a constant term, a number, that's a polynomial technically. I can have a negative coefficient out front or an x value to some power here. I can have a radical coefficient. I could even have pi x squared or something like that. Those would all be polynomials. However, anything with a negative exponent is not a polynomial. A rational exponent, a radical, exponent, or variables in the denominator, none of those things are technically polynomials. Now, some of the characteristics of polynomials are that they have smooth curves and are continuous. Now, you want to make sure you understand the characteristics of a polynomial. This is going to be something that's really important when we get to calculus and we talk about continuity and continuous functions. So polynomial functions have smooth curves, no sharp edges, and they are continuous, meaning you can draw it with your pen or pencil without picking it up. There are no holes or jumps or anything like that. Now we want to talk about the end behavior of a function. Okay, I'm going to need to zoom out here a little bit. You'll probably be able to see this better on your paper than in this video. But looking at these functions here, if I have something where the arrows, the ending arrows, go in opposite directions, then this is something of an odd degree. So notice these, we have the arrows going in opposite directions here. One is going up, one is going down. So our degree of our polynomial is odd. So the highest exponent is a 1 or a 3, 5, 7, so on. Now if these ending arrows go in the same direction, then that means that it's even. So like x squared is our degree, or to the 4th power, 6th power, so on. Now the other thing we want to pay attention to is which direction our function is running. Notice this function is running in a positive direction. That means our a value, our leading coefficient, is greater than 0. If our leading coefficient is less than 0, then our function is running in a negative direction. Now, same thing with even degree. If our leading coefficient is positive, then both arrows are pointing up. But if we have our leading coefficient being less than 0 or negative, then both arrows are pointing down. Okay. Just a brief, easy example of each one of these. Something where both arrows are running in a positive direction, maybe something like 3x cubed. Something like this would maybe be negative 4x cubed. Okay. Something like this might be, we could say 1/2 x squared. Something like this could be negative 3x to the 4th power, something like that. Okay? All right, going and flipping the page. Now let's look at some examples here. It says, use the leading coefficient test to determine the end behavior of this function right here. So all we're interested in is the largest term. We don't need to multiply everything out, but we need to know what the largest term is. So looking at this polynomial here, we have an x cubed term. And then from this, because it's squared, the largest term we're going to have is x squared. And then here we have an x. So our largest term is going to be negative 4x cubed times x squared times x, which is negative 4x to the 6th power. Now, this degree is even, and our leading coefficient is negative. So what that means is both ending arrows they're going in the same direction because it's even, and they're going down because it's negative. So both ending arrows are going down. So we want some sort of phrase here to explain what's happening at the end of our function. Now we can talk about the zeros of a polynomial function. The values for x with f of x is equal to 0 are called the zeros. A lot of times we have other terms we use, zeros, roots, solutions, x-intercepts. Those all are really referring to the same thing. Now we can talk about the multiplicity of zeros, meaning the number of copies of a zero. And if our multiplicity is even, then the graph touches the x-axis and turns around at that value. If our r value is odd, then the graph crosses the x-axis at r. Okay, so let's look at an example of this problem. In my opinion, these are some of our easier problems. You want to take advantage of these questions on your test. So we have this polynomial right here, f of x. And just by looking at this, we can tell that our graph has roots or zeros at x equals -1 and at x equals 3/2. Okay, so all I did was set my roots equal to 0. Now we can write what the multiplicity is of these roots. We have one copy of this root and we have two copies of this root. And that's all we've got to do other than saying what happens at these values. Now remember, if our multiplicity is even, it touches the x-axis and turns around. So this one touches the x-axis and turns around. And then this one is odd, so if our multiplicity is odd, then it crosses the x-axis. Okay. Now this next thing right here is something that we won't use a ton in pre-calc, but it will be something that is useful for us in calculus. This is called the intermediate value theorem. So the intermediate value theorem, or IVT, okay, what that tells us is that if I have some y value up here and I have some y value down here, so one above the x-axis and one below the x-axis, or in other words, something positive and something negative, that means that if this is a polynomial, there has to be a point in between these values where f of x, or our function, is equal to 0, where the y value is 0. That's all the intermediate value theorem is really telling us. We can use that to show that there is a 0. So I'm going to go ahead and look down at our first example here. It says, show that the polynomial f of x has a real solution or a root between 2 and 3. So in order to show that, we want to look at f of x at 2, and we want to look at f of x at 3. So plugging in those values, 2 cubed minus 2 times 2 minus 5 is equal to -1. And then we have 3 cubed minus 2 times 3 minus 5, and that's equal to 16. Well, we have a positive 1, we have a -1, so what that means is there must be a real root between 2 and 3. And that's how your answer should be phrased, and I should see this evidence right here. So again, I'm going to go ahead and flip the page here for us. And now we can talk about turning points. So the turning points of a polynomial function. Okay. And that's where the graph turns, and it's going to be at most, if we have a polynomial, let me go ahead and fix this here, that should be of degree n, then the graph has at most n plus 1 turning points. So if my polynomial has degree 5, then I have at most 4 turning points. Okay. So we've talked about a lot of the details now, and all of these details about polynomials really are bringing us to being able to graph these complicated polynomials. And I'm not going to read through all of these steps because I know that you can read through them on your notes. But what this is a list of things to try in order to help you to graph polynomials. So if you're looking at a polynomial and you have no idea where to start, this is your list of things to go through to help you figure out what the graph looks like, because you guys will be graphing these without your graphing calculator. So we want to use the leading coefficient test, look at x-intercepts and y-intercepts. We can use symmetry, we can use turning points, even in odd functions, and all the information that we've learned in this chapter so far. So let's look at an example here. We have f of x equals x to the 4th power minus 2x squared plus 1. And you know what? We have a couple examples. Actually, we just have this one example here. Hopefully this video won't be too long for you guys. But we have this polynomial here, and we have a degree of 4. So we know that both arrows are going in the same direction. And because my leading coefficient is positive, that means that both ending arrows are going up. So I know that much about my graph. Okay. Now I can also try factoring it to find my x-intercepts. So I have x to the 4th power minus 2x squared plus 1 equals 0. This will give me my x-intercepts. So then I have x squared minus 1 and x squared plus 1. I'm sorry, minus 1 again. Equals 0. And this factors to x plus 1, x minus 1, and this does the same thing. And I can rewrite that as x plus 1 squared and x minus 1 squared. And that means I have a root at x equals 1 and x equals negative 1. And they have multiplicity of 2. So that means it touches and turns around. So from the details we've just gained, let's go ahead and see if we can start to get an idea of what our graph looks like. So I have, so far I know degree 4, so I know I have ending arrows going up. And I know I have roots at negative 1 and 1. And I know my graph touches and turns around there. So that's the stuff I know so far. Next thing I can look at is what is my y-intercept. I can plug in 0. Well, if I plug in 0, then I get 1. So I know now that I also have the point 0, 1. So far, this is what I know about my graph. Now, I also know that I have at most 3 turning points. Because if my degree is 4, then I can have at most 3 turning points. So if I'm going up towards towards infinity here, I can come down, turn once. I'm turning here once, turning here once, and turning here once. So I've used all my turning points. I have no more turning points. So this is what the rest of my graph must look like. And if you're not sure, you can always make a table of points here and plug in more values. So that's the end of section, I think we're on section 3 here. And hopefully you can get some practice graphing these functions in your homework.